Hi girls, hopefully this works well and you can hear me fine. Now this is an assignment, so I'm clearly not going to do it all for you, but I will give you some hints on some of the problems. Alright, you said the issue started around question 6, so I'll take one of the examples from question 6, let's say this one, and we will graph that sketch showing all the features clearly. Alright, now rather than you putting up with me sketching graphs, I will do this online. If you were sketching graphs, then you could do it by hand or in your head imagine what would happen. So in your head, imagine starting with a sine curve. So starting with a sine curve looks like that. We've seen sine curves before, that's fine. Then you might notice in the question that it says, well, it's 3 sine of something. Alright, well what does the 3 do? The 3 increases the amplitude by a factor of 3. It basically multiplies the entire thing by 3. Note, the intercepts are still happening in the same place. The peaks are still happening vertically above each other. They're just 3 times extreme. Instead of peaking at 1, it's now peaking at 3. Fair enough. So then we look at the next part. Well, inside here, there's a 2. Now, what does the 2 do? The 2 increases the rate at which this cycles through. So it increases the period, or rather decreases the period. So we've still got an amplitude of 3. But now, instead of in 2 pi, so from here to 2 pi out being 1 cycle, here to 2 pi becomes 2 full cycles. So now the period, instead of being 2 pi, the period is now 1 pi. Alright, then go back to the question again. Alright, so inside the bracket is x plus pi on 4. Well, what effect does pi on 4 have? Pi on 4 is a horizontal translation. So we've still got a period of pi and an amplitude of 3, but now it all happens pi on 4 before it was, where it was before. And finally our last step is -5. Everything we had before is just dropped down 5. So for example, if you wanted to take this as the base, and you could imagine a peak here being at the point pi on 2, pi on 2, 3. Alright, now it becomes pi on 4, 3. We're just looking at this peak. Instead of pi on 4, 3, we've subtracted a quarter pi. So now it's 0, 3. And then we subtract 5. It is 0 minus 2. So imagine starting from a simple one, and then tracking what each of the changes will do for a couple of the points, and that will let you sketch the graph. That technique will hopefully help you with the others also. Start from the most basic function, build on from there. Alright, question 7. Question 7 is a good one. So question 7, it's given us here that sine x is equal to -5 on 13 for x between 3 pi on 2 and 2 pi. For this, we once again are thinking of a unit circle, and we're in the 4th quadrant. Now, unit circle, we assume the whole time that the radius is 1, but it doesn't have to be. And here, a cool trick lets us answer this one nicely. So let's say I put a line in here, and I'm going to say the length of that line is 13, and this length here is 5. Now, if we take this theta here, this angle, sine of that angle will equal opposite over hypotenuse. So when we say sine x is -5 on 13, well, then what we're saying is sine of this angle here is -5 on 13, so we can set it up in a triangle like that. Alright? Which means, using Pythagoras, we can label the other side as well. If we have a 5 and a 13, this one here will be 12. So if we don't know what x is, we can still write cos x. Now, given we worked out this triangle from the original sign, cos x will be, well, adjacent over hypotenuse, so 12 over 13, and because it's in that region, it's positive. Tan x will be opposite over hypotenuse, so that'll be, opposite over adjacent, 5 on 12, and tan in that region is negative. Oops, I just gave it to you. But the cool trick here is not having to use a unit circle if you don't need one. Alright, question 6. I'll take one of the examples. That's this one here. And we'll go about solving that. So what this is saying is that for the unit circle, at some point, well actually 2 points, and we're only looking within one rotation, at 2 points, this length here and this length here will be a half. And we know that that half occurs excuse me, when we know that this occurs when this here is pi on 6 from our special angles. Alright, so what we're really saying is that sine of some number equals a half. This one in here must be pi on 6. Alright, so therefore for what values of x does this here return a pi on 6? Another solution would be, using red, that's the whole way back, so 5 pi on 6. So for what value of x does this return 5 pi on 6? And from here you can set up a pair of equations saying 2x plus pi on 3 equals pi on 6, or you'll get your second solution from 2x plus pi on 3 equals 5 pi on 6. And I'm sure you can follow through and find those two. Alright, looking at this one here. I can't do them all for you. Well, I won't do them all for you. Linear approximation for sine x. Find the approximate value of sine 2.7. Now this one surprised me a little, because linear approximation is typically used in conjunction with calculus. You use calculus with it. So I'm wondering, have you guys seen that before? And especially, have you seen that dash? I know you're meant to start calculus in year 11, methods, but I'm not sure you have yet, so I was kind of surprised to see this question. Alright, if you haven't, fortunately the logic's quite easy. For values of sine x very close to 0, so when this value is approximately equal to 0, that's meant to be approximately equal to 0, when this value is approximately equal to 0, we can look at the sine curve here on the right and see that for very low values, sine x is approximately the same as the line y equals x. So a linear approximation of the sine x curve is y equals x. So here, the approximate value of sine of something close to 0 could be essentially following the line y equals x. Instead of y equals sine x, for x at close to 0, you might as well just write this as y equals x. Therefore, your linear approximation is, your result is 2.7. Makes sense? What that's saying is, for the sine curve here, if we go across 2.7, then the distance we head up using the green will be approximately distance equal to the distance we head up using the red. And because the red is much easier to work with, we approximate it to be linear. Alright. If you're around a table, I'm trying to imagine you guys either nodding or shaking your head really confused. Hope that makes some sense. And when cosine is equal or very close to 0, at the top here, you might as well just think of it as 1. So for example, cosine of 1 degree is basically 1. Cosine of negative 0.4 degrees is basically 1. So either side here, when theta is close to 0, cos theta is basically 1. Alright, so given that the solution of sine x take 4x plus 1 is small, use the linear approximation for sine x to obtain an estimate of this solution. Alright, so here what we do is we say, well, if it is small, we can say that for y equals sine x, we simply sub in x. So we're saying that for small values of x, this is the same as this. And therefore your equation becomes something like this. X take 4x plus 1 equals 0. Solve away. Alright. First step here, draw a graph. Using similar technique above, you can draw a graph that looks like this. So what that's saying is that at 2 AM in the morning, so on your x-axis here is time between 0 and 24. At 2 in the morning, so time 0, it is negative 2 degrees. Sounds about right for this town. So that's the first question. What was the maximum temperature and what time did it occur on Tuesday? Well, once again, you look at the graph. The maximum temperature was 18 degrees and it occurred at, that's 10 o'clock, so 12 o'clock on Tuesday, 12 PM, midday Tuesday, etc., etc. All right, I hope that helps. Hope this works. Thank you very much.